Goldwasser on the research that led to her Turing Award, so it was really very interesting. So for that reason, we're getting started a little bit late, just a few minutes late today. But this is also going to be a terrific talk, just like the other one. Now, the title is The Benefits of Mixed Signal Computing for Artificial Intelligence. But actually, mixed signal is just a surrogate word, and what it really means is analog, okay? And so, we have, of course, we have machine intelligence. We have machine intelligence accelerators. For example, have made NVIDIA a very powerful company. But they're taking very much a digital approach. But what has come about now is, as people understand the machine intelligence algorithms a little bit better, they get to realize that maybe there's a chance to do some of the key functions, like, for example, the linear algebra part. Maybe there's a chance to do that analog. Now, if this happens, of course, it's a very competitive field, so it may not happen. That's why we have to hear from Dave Fick, our speaker. But if this happens, this would be the first reemergence of analog computing into computer science for about 60 or 70 years. So it's a very important development. And you might question whether this is really likely, given everything that's happened in the past 60 or 70 years. So I'm really looking forward to the talk. Now, Dave is the CTO and co-founder of the company that is doing this. So the company is called Mythic. It is a startup that I think it started in Michigan, but has since moved to the Palo Alto area to be, well, I suppose, to be closer to the source of money. They have plenty of money, and I suppose they're behind the eight ball. They actually have to deliver hardware. The investors are expecting hardware very shortly. With that, I want you to save up your questions, think about this, and let's give Dave a very warm welcome.
Well, thank you for the kind introduction. Just a little, slightly more about who we are. Mythic is focused on edge AI in particular, and for inference. So artificial intelligence has both the training side and inference side, and we're very heavily focused on the inference side, and particularly in edge. And we're going to show why this is important in each of these cases. We were founded in 2012 by Mike Henry and myself. We're basically, we both finished our PhDs. We wanted to do postdocs, but instead of begging our advisors for money, we went out and got R&D contracts from the Air Force, and then came and gave them money, which kind of put us in the driver's seats for these projects. Since then we've raised about $55 million from DFJ, SoftBank, Lux, and so on. We're up to over 60 employees. I think we're at about 70 now. So of course we're looking for great people. So if you're interested in this sort of technology, we range all the way from device physics all the way through DNN applications. So 2012 is an interesting year. Anytime you hear these talks by like Bill Gates and whatnot about getting lucky. So this is how we got lucky. Is in 2012, when we got started, it was right after AlexNet came out. So only a few months before we started looking at machine learning, AlexNet had been published, and they showed this huge improvement in, he showed this huge improvement in classification for ImageNet, a large competition with 1,000 object categories. And since then, things have really taken off. And one of the questions I often get is, why is machine learning so exciting? Like, AI has been around for a long time, computers have been around for a long time, and the thing that has really changed in this field is the idea of intuition. So the computers that we have today are really fast at procedural algorithms, which are effectively like describing a flow chart. You do step A, you check something, and step B, and then you have this conditional, do you go left or right in the flow chart. We can do that at gigahertz speeds. But for some tasks, there are no effective procedure for determining the answer. And so this is, for instance, trying to classify a picture. You have this random matrix of numbers, and you have to determine what that picture is. And there's no algorithm for determining how to figure out if it's a tulip or some other object. So what neural networks do is they provide this intuition for these problems where we haven't been able to figure out a procedural algorithm how to solve them. And so they're kind of covering for us. The problems that machine learning is taking on for us are ones that we can't figure out how to solve. And so now we've created some sort of computer to solve the problem for us instead of us solving it directly. And the really interesting thing about that is everyone talks about like the machine learning models like AlexNet and ResNet 50 and so on, but those are a tool. The actual thing that you're describing your application with is the examples that you've described the application with. So you could almost call it like your machine code, or sorry, your assembly code is this set of examples describing what you want the algorithm to do. And so today, and you can kind of think of it as today we're all programming an assembly code where we compile millions of examples, and maybe tomorrow we'll have a much better set of tools that we don't have to work in assembly, we can work in more like a C environment. So just kind of touching on this again, remember the reason why we need intuition is because we will have some scenario like this where we have sorry, I'm trying to find a pointer here. We have this matrix of numbers, and now we want to label that one way or another. So the question is, how do we do that? This problem is a lot harder than just labeling just a tulip. I'm trying to provide some motivation of why we care about edge inference. So, ImageNet has actually 1,000 different object categories, ranging from tulips to, you can kind of see here on the right, you have mites and container ships, so there's a very large range of scale. You have different types of jungle cats here. Some of us wouldn't even be able to tell the difference between a leopard, a jaguar, a cheetah, and a snow leopard. And so the number of object categories actually makes things much more complex. And today, there's a new version of ImageNet that goes up to 22,000 object categories. So the problem can get very large from the number of object labels that you're trying to support. The other dimension that the problem gets very complex is the type of labeling that you're trying to do. So when you're thinking about labeling an image, you're usually thinking about classification where you're just labeling the whole image as cat, which is basically saying that the dominant object is a cat. And then this can get significantly more complex as you try to put a bounding box around the object, detect multiple objects, and then finally try to put very tight bounding boxes around the objects. And now you can see, even in this example on the right, we haven't actually labeled all of the objects because there's grass. You could label individual blades of grass. There's bushes. You could label the leaves on the bushes. You have a bucket here. Even on the animals themselves, we've labeled this puppy as a dog, but we didn't label its eyes and nose and its collar or what type of puppy it is and so on. So the reason why I'm bringing this up is between these two dimensions, we're actually not anywhere near the amount of capability or the amount of performance that we want out of machine learning. So even though we're able to label a couple cats, a duck, and a dog in this picture, we are there's a huge gap between what we're able to do now and what a human can do. And a human can label thousands, well, probably not thousands, but maybe hundreds of objects hierarchically and relate them relationally in this picture and be able to tell you far more than just cat, duck, and dog. So I'm going to touch a slight amount of background on how these algorithms work. So let's say we have some image. We're trying to look at the AlexNet architecture here, where AlexNet is a neural network model. We have an incoming matrix of pixels on the left going to some sort of label on the right, which is leopard. Now remember, AlexNet is doing the ImageNet category, or ImageNet problem where there's 1,000 different object categories. So when we say 75% here, that means that we have 1,000 different scores, and the leopard score is 75%, and all of the other scores sum up to about 25%. So the way these pictures are usually drawn is something like this. And the interesting thing about this diagram is, well, one, if you're already familiar with AlexNet, you'll know this is a simplified version, so just ignore that. But then the other one is usually they show these volumes, and these volumes are not actually the neurons, which is something that's slightly confusing about the pictures. These volumes are actually the intermediate data stages between the different stages. So actually the image here on the left is represented by this matrix. It's a 227 by 227 by RGB. That's what the 3 is. And then the 1,000 object scores is on the right in this vector. In the middle here is the intermediate data between the stages. And then the neurons are actually these little arrows kind of between the stages. And so this is where we're doing the matrix multiplies. So inference is the process of taking this image and running it through all these matrix multiplies and getting your output vector. And then training is the process of doing the calculations to figure out what all these weights should be. It's done through a stochastic gradient descent. So I'm showing here AlexNet, but one thing that you should realize is that all of these applications are fairly similar. So in each example, or in each application, we're doing some sort of mapping process where we're mapping an input to an output. And then the way we describe our application is not by a procedure, but we're describing the algorithm through a series of examples. So we're saying, here's 10 million examples of what I want you to do. Figure out how to do it. And if you think about it, that's kind of how you interact with a person. You don't necessarily provide them a procedure. You might provide them a handful of examples of how to go about doing a task. So in decision making, this is probably the most important one for the public to feel like artificial intelligence is actually here. So when you talk to Siri and ask Siri to do something for you, this is where currently Siri will have a list of instructions or a list of things that she's able to do, and she's just checking that list to see if you used any of the correct command phrases. In the future, what we want is Siri to actually take your command, intelligently process it, and map it to some action. And there's a slight difference there where if you, in the former case, if you misword something, Siri is going to just balk. In the latter, where we're actually using AI, Siri will be able to figure out what you meant. Actuation is mapping physical goals to motor control. So this is like Rosie the robot. Speech processing is mapping waveforms to words and phonemes. And then text-to-speech is, you could have Microsoft Word do this 10 years ago, but it'd sound like Stephen Hawking. And so this is an algorithm for providing very lifelike speech. All right. So that was the AI backgrounding case for those of you that aren't familiar with the space. And so now I'm going to talk a little bit about what is the motivation behind this mixed signal system. So the observation that we made is that, one of the most obvious observations about the AI space, or the neural network space, is that these deep neural networks are largely multiply accumulate. And so what that means is that when you look at a neuron stage, you have every stage is represented by this matrix of weights. And then what the goal of the way the algorithm works is you take your input data for each stage and you multiply that input data by your matrix of weights. And that generates a matrix of outputs. And the way you generate each of these outputs is this pretty simple equation where you're just taking each of your input elements and multiplying it by one of your weight coefficients. So the key operation here is this multiply accumulate, and in many cases these are actually just 8-bit numbers, so it's a very simple operation. The key though is that there's actually a very large number of these multiply accumulate operations. And so this creates this figure of merit of how many picojoules does it take to execute a Mac, because if you're talking about the power draw of the system, you can multiply your picojoules per Mac by how many billions or trillions of Macs you have to do to process an image, and then that'll give you how many joules of energy it takes to process a single image. And of course, if you then 30 frames per second or whatever, then you have your power. So when you look at these sorts of equations, though, you can break down the data into two different types. You have your weight data, which are these coefficients, and you have your intermediate data, which is your input data and your output data to each of these neural network stages. Now the weight data, these coefficients are static, and these are what was trained by that neural network training process, which is typically done on a giant server. These two different types of data have different properties to them. So if you look at a stage that, say, has 1,000 inputs and 1,000 neurons, then you'll have 1,000 inputs, 1,000 outputs, and 1,000,000 weights. So there's a factor of 500 difference in how much intermediate data is involved at this stage and how many neural network weight coefficients there are. If we look at a single piece of input data, you'll see that it gets reused for each of the 1,000 outputs. And so this becomes very important when we're trying to analyze the energy efficiency of the system. Because if you look at, if we're trying to compute this, say, in like a SIMD unit or other DSP, we have to access all of these inputs and we have to access all the weights. And those come from SRAM. And reading about a byte of memory from SRAM costs about a picojoule of energy. And so you take that picojoule, and let's say we read x0, and that takes 1 picojoule. So that's cost us, and we want to know what that 1 picojoule comes out to in terms of picojoules per mech. Well, there's actually 1,000 different mech operations using the picojoule cost of reading x0, and so therefore the energy contribution of reading x0 is only 1 femtojoule of energy. So reading x0 is not actually is not a significant factor of our picojoules per mech of the system. So we can say in general that intermediate data axes are heavily amortized. So every time we read an intermediate piece of data from SRAM, we can actually effectively divide that energy cost by a factor of 64 to maybe 1,024, depending on how many neurons are using that data. The weight data, however, is not actually amortized in the same way. So if you look at these equations, like if you look for A0 here, there's only one place that we use A0. So the energy for accessing those weights is not similarly amortized. Plus, that data, the weight data may actually exist off-chip in DRAM, someplace that's really expensive to access. And because of that, we don't have that same energy amortization. So if it cost us 1 picojoule to access a byte, and there was 1 picojoule to access x0 and 1 picojoule to access a0, then the energy contribution from this mech, ignoring the actual calculation, would be 1.001 picojoules, where almost all of it came from accessing a0. So accessing the weight data is our major cost for running neural networks. So here's a few different networks. AlexNet is, of course, very important for historical reasons. Then there's the ResNets, which are extremely popular. VGG, this is also very popular. And then OpenPose is a similar network where you're trying to determine the pose of people in the image. And so in each of these, you can kind of see that there's many tens of millions of weights in some cases, up to over 100 million weights in VGG's case. And so there's a question of how do you deal with all this? There's a huge number of weights that's very hard to fit in an edge solution. You might only have a few megabytes of SRAM on your system, and so now you're trying to fit maybe tens of megabytes of data in the SRAM. You've got there's additionally billions of MAC operations that you have to perform, which might be trillions by the time you get through their 30 frames per second. And so how do we do this with high energy efficiency, high performance, and an edge power budget? And so I'll kind of motivate this a little bit further by looking at thermal limits. So if you go and look at like various applications in the edge, you're typically limited by how much power you can draw in a form factor. And so we're going to use numbers here from ResNet 50 at 4K image resolution. So if you get like a Nest Cam IQ, that's a 4K camera. And this is about 580 billion max per frames. So this is almost a trillion operations just to process one image. And so the figure of merit I mentioned was picojoules per mech, and that gets that's going to interact with this thermal limit of 5 watts. So if you touch a Nest Cam IQ, the casing is actually metal, and they're using that to dissipate all of the heat out of that system. And it's a very small package, so it's kind of hard to dissipate a huge amount of heat because there's no fan. And so you're limited to about 5 watts on the max side, and it's going to be hot to the touch. And so if you're drawing 50 picojoules per Mac, then if you divide 5 watts by 50 picojoules per Mac, then you get about 100 billion Macs per second, which for ResNet 50 at 4K resolution is only 0.17 frames per second. So this is not going to work for many applications where you can run at 1/5 of a frame per second. Similarly, with 10 picojoules per Mac, this is at 0.9 frames per second. And if you can get all the way down to half a picojoule per Mac, now you're going to be up to about 17 frames per second. So if you can get your energy efficiency good enough, then you can take your system from being unusable to usable for these applications.
And so the application you had in mind was image recognition and a Nest doorbell?
This is for one of the Nest security cameras. So the security camera application might be around 5 watts. And then you can imagine maybe for like a vehicle, you might have like a dozen of these cameras around the periphery of the vehicle.
I mean, these are good for comparison since ResNet is so 50 so standard. But have you looked at the more mobile, since you're focused on the edge, have you looked at some of Nets that are more focused on edge applications?
For the video, maybe you can repeat the question.
So I think you're asking about heavily compressed models.
Let's just say smaller models.
Yeah, so there's smaller models, and so what he's basically pointing out there's these efforts to make models more efficient. So if you go back here, you have AlexNet, ResNet 50, VGG 819. These all have wildly variable numbers of weights and wildly variable numbers of Macs, but they actually don't perform wildly different. And so some networks are inherently more efficient than others. And so the one I chose here is ResNet 50 because there's many of the prospective customers that we talk to are highly interested in ResNet 50. It's a good starting point. And that's about 3.5 billion Macs for 224 by 224 resolution. And of course, this goes up to 580 billion once you get up to 4K. So as you can see in this case, this is getting up to barely a usable frame rate. The point I was trying to make earlier was even if you had a much more efficient model, let's say you was 10 times more efficient, if you go into these sorts of dimensions about being able to do far more object classes, being able to label at a much finer granularity, being able to capture motion data, and so on, there's always going to be more that you want to do. If the performance is available, there is clearly more in the horizon to do in the AI space. So we think that if we can provide 10 times more performance, that people will find something to do with it. So
you're assuming, you mentioned 8 bits resolution, you're assuming perfect resolution, perfect computation? Approximation?
How do you mean?
Well, maybe we can hold the questions for the question period because we're not picking them up on the microphone.
Okay.
Please go ahead.
All right. And then, so for an automotive vision system, if you look at the extreme cases, they might go up to 100 watts. A lot of the larger competitors that we're looking at are around 70 watts. Then these numbers go up quite a bit because you have so much more power, so you have a lot more performance available. But remember that this is being shared among about a dozen camera systems. So if you've got a vehicle with 12 cameras and they want to go to more cameras because maybe one gets muddy and so you want to have a redundant one, this doesn't actually go that far, even with a very large power budget. And there's a lot of desire to go down to below 10 watts. So this performance is also very important to accuracy. So the more, when you're talking about resolution, for instance, if you're running, this is examples where we're taking the same video and running single shot detector, which is a multi-object labeling system. It's just doing 2 object classes, cars and traffic lights. And if you run this at 2 different resolutions, one with 300 by 300 resolution, one with 700 by 700, you can see that the 700 by 700 resolution captures or is able to recognize far more objects in it. And this is without changing the algorithm at all. It's just about changing the resolution of the data going in. And you can kind of imagine that for yourself. If you're trying to look at this picture and, as a human, it's going to be harder to recognize the traffic light for yourself than in the lower resolution than it is in the higher resolution. So the reason why I bring this up is because one of the questions we get is about accuracy in analog computing. And what we'd like to say about that is if we can provide 10 times or 100 times more compute horsepower, then you can translate that to accuracy by running at higher resolution or by running at higher performance models. So so there's multiple ways of reducing energy consumption, and this actually comes out in a variety of options. And so there's they come into like 2 main categories. There's weight reuse, and then there's weight reduction. So weight reuse is about trying to find the amortization that we use for the intermediate data. We can do that by focusing on ways of reusing the weight data as well. So convolutional neural networks, for instance, reuse that weight data by taking the same set of weights and stamping it across the image, so using it as a windowing operation. And then we can actually build specialized structures around convolutional operations to make that more efficient. We can focus on large batch, which means that we're going to process multiple inputs in parallel. So if you process, say, 10 inputs at the same time, then when you read that weight from memory, you can reuse it 10 times and get that 10x reduction. On the weight reduction side, we can shrink the model, so we can do things like compress the network, like using a SqueezeNet. We can compress the model. And there's a couple different ways of doing that. One is to use sparsity, so creating highly sparse matrices, or we can use literal compression to store the matrix more efficiently. And then finally, we can use reduced weight precision, so we can go from a 32-bit floating point to an integer that might be 2 to 8 bits. So each of these have some drawback to them. On the weight reuse side, focusing on CNN might not be the best fit for every application. Convolutional networks are taking advantage of certain properties of the data, which is an XY spatial property where we know that all the information is related to each other in a particular way. But for instance, working with time, you don't have that same relationship, and so you prefer to use recurrent neural network in order to manage time information. Large batch may not work for edge. In many cases, like we're talking about the camera system, we work with a batch of 1, and so we can't necessarily have 10 cameras feeding into the same location. On the weight reduction side, each of these have you don't get something for nothing. So they're each going to reduce their accuracy by some degree versus using the full fidelity model. So one of the key decision points for a system is whether or not to use DRAM. So if you're starting your new neural network processing startup, and you're going to get into the office on day 1, and the first question you have to answer is, are we going to use DRAM? And so if you use DRAM, you can fit arbitrarily large models, and you don't need as much SRAM on your chip. So those are some pretty big benefits. But the drawbacks of adding DRAM to your system is that anytime you read those weights, as I mentioned earlier, from DRAM, there's a huge energy cost to doing that. DRAM also has a very limited amount of bandwidth. For instance, when you look at on-chip interconnect versus DRAM interconnect, a single on-chip link has as much bandwidth as your DRAM link, and you might have many of those on-chip links. So the bandwidth to DRAM is very tiny compared to what you can do on-chip. And then finally, your system performance and energy efficiency are going to be highly variable depending on whether or not they're actually using that DRAM and to what degree. So if you have an application that heavily uses the DRAM, it's going to be slow and inefficient. If you lightly use DRAM, then it's going to be very fast. So because of that, you'll see neural network processors break into 4 common design points. And so we split these into enterprise and edge, and then with DRAM and without DRAM. So in the enterprise space, these are typically reticle-sized chips, or even larger than reticle-sized chips, where the amount of SRAM is in the order of tens or hundreds of megabytes. The power is usually in the order of 70 to 200 watts. And then these have a lot of nice capabilities like floating point precision. They have really high accuracy, really high performance. And then the energy efficiency ranges from about 25 picojoules per Mac, which is kind of like a GPU, down to around 2 picojoules per Mac, which is more like an IPU that you'd see from one of the newer startups.
Clarification?
Yeah.
Could you please repeat what is the key difference between enterprise and edge?
So enterprise is in a server environment. And so you might have like a server card that draws like 200 watts in a big data center like at Facebook or Google.
Okay.
And then edge is like a smart camera or a vehicle, something where you basically can't draw 200 watts. So on the edge side, this might be like your smartphone. Your Snapdragon processor will typically have less than 5 megabytes of SRAM. If you're drawing power, it needs to be below 5 watts. And then this is where things get interesting, is because we have a small amount of memory and we have a small amount of power. So we need to somehow deal with that, right? We can't fit like a 20 megabyte model in the system and run very quickly. So typically we'll use, in these systems, we use moderate to heavy sparsity depending on how much DRAM we're using. The precision is usually integer at 8-bit or less. And then if we don't have DRAM and we have to fit the entire model inside of only a handful of megabytes in the chip, then that's going to make it so we have very poor accuracy at that point. And then similarly, the performance in these systems is going to be very low because there just isn't that much capability in these systems. They get to a pretty reasonable energy efficiency, but not as good as the enterprise, because remember, enterprise has the batch processing that they can do in parallel. So there's things that they can take advantage of in enterprise that we can't take advantage of in edge. So what Mythic does is we introduce a new memory class, the non-volatile memory, for use in AI. And what that's going to allow us to do is be an edge system, but get the sort of the accuracy and efficiency that you see in enterprise. And so we do that. I'll talk about that and how we do that in a minute. But basically, we have that edge profile where we have low power, we have no sparsity, and when we have integer precision, so the whole system is going to run an 8-bit integer precision, then we can get that great accuracy, performance, and energy efficiency. Additionally, we can do this in a 40 nanometer process versus the 7, 10, or 16 nanometer processes that we see for the systems that we're describing here as competition. So the way Mythic does this is we introduce what we call the matrix multiplying memory. And what this is going to do is allow us to never read those weights. So the energy cost of reading the memory is 0 because we're not going to read it. And we're going to do that, and the energy we do pay is only directly for the Mac operation itself. By having this structure, we can eliminate the need for batches of greater than 1. We can eliminate the need for CNN focus, for sparsity or compression, and for NERF DNM models. So we can have everything that we wanted to have before by introducing this new type of memory. And the way we'll do this is by using mixed-inlet computing on embedded flash. So going back to our matrix multiply calculation here, what we're going to do is represent the neuron weights using a grid of flash transistors. So the way this will work is each one of these elements, each of these matrix coefficients is going to be represented by a charge on a flash transistor, and we're going to vary the threshold voltage of that flash transistor to represent each of these matrix elements. In this picture, the flash transistor is represented by a resistor, and what we're doing is we are treating the flash transistor as a variable resistor, and we're going to use the standard V equals IR current equation in order to get the math that we need. So the orientation of the matrix is the same as before, so the neurons are these vertical columns, and so you could think of these wires here as the bit lines. The inputs are going to be coming in from the left, so we've got X0 going across, so these are kind of like the word lines. And then our matrix coefficients are the resistances here. So if we look at the voltage across one of these resistors, that's going to generate some current depending on the voltage input and the resistance here. And those two multiplied together will give us our current. The way we get in and out of the analog domain is using a DAC, so a digital analog converter on our inputs, and an analog to digital converter on our outputs. So the rest of the system is in the digital domain, and then the analog compute is just within the memory structure itself. So because of that, we have a digital top-level architecture, which is why Mythic is called mixed-signal computing and not analog computing, because we want certain properties of digital that are where digital is strong. So digital is really strong at interconnect, so communicating across the chip is much safer and easier to do in a digital encoding scheme than an analog encoding scheme. SRAM can be used for intermediate data storage, so it's easier to store information in the digital domain. And then it's also easier to provide programmability. So we can take XLA and Onyx, which are ways of specifying neural networks, then we can map those onto our intelligence processing unit quickly and easily. One of the things that we get asked about is the analog input side of things, and what we're actually doing for our very first generation of the system is we're using a digital approximation technique instead of creating the DACs, and this is to improve our time to market. And so in the future we'll have full DACs here instead of the digital approximation, which will provide us a further improvement over what we're showing today. So the way the rest of the system is organized is through a tile-based architecture. So we have this memory structure that I mentioned before, the matrix multiplying memory, which has the analog compute inside, and then the digital to analog and analog to digital conversions. And then the rest of the tile includes a RISC-V processor for providing programmability and controllability, SRAM for intermediate data storage, a SIMD unit for providing vector operations on the data that's outside of the matrix multiplying operations. And that way we don't have to have the RISC-V processor actually process any data. And then a network on chip router, so we can have the tiles talk to each other and provide a top-level interconnect. These tiles go down in a big grid on the chip, and so neighboring tiles would talk to each other through this network on chip router. We can support multiple applications on the system by mapping them to different regions of the chip. So you can kind of think of this like an FPGA, where you have a mapping of your application into a grid of physical hardware. And if you want to support multiple applications in your FPGA, you can segment the FPGA into multiple regions. So this system is highly configurable and expandable since it's tile-based design. And so we have our initial product, which has a 50 million weight capacity, PCI Express 2.1 with 4 channels. This is coincidentally as much bandwidth as you need to process 4K video. And then we have a basic control processor that's going to be managing this system. We envisioned some customization, so if a customer came to us and said they wanted a different variant of the system, since it's a tile-based design, we can actually very quickly tape out another version that goes up to 250 million weights. We can include more PCI Express channels, add support for USB 3, and then there's also the possibility of adding direct audio and video interfaces, or even more advanced ARM core. So the way this will integrate into the system is if you go and look at like a NESCAM IQ, you have a host SoC, which I believe is a Snapdragon in that system. There's it'll talk to the image sensor, it'll have DRAM and the Wi-Fi connection. And then what our chip is providing is an offload engine to that host SoC. So you can take oops, I don't know what I hit. So you take the image data coming from the image sensor, it gets piped over the PCI Express port. The Mythic IPU is running that inference model, which is specified using TensorFlow, Caffe2, PyTorch, or other applications. And then the IPU will send the inference results back, which is that vector of labels, over the PCI Express port. We can also support multiple IPUs in the system. So some applications might require more performance than what can be provided by one chip. And so you can always buy more chips and get more performance. We're advertising half a picojoule per Mac is our figure of merit. And one thing we'd like to point out is that this is for real applications and accounting for everything in the system. So if you take that half a picojoule and make a pie chart, about half of it is the analog compute on the system. And then the other 3 parts are digital storage, the control logic, and then the PCI Express port. And the PCI Express port, we're actually accounting for both sides. So not just this chip's power, but also the power drawn by the host SoC. This is for a typical application like ResNet 50 running batch size of 1. And it's also for running in 8-bit mode. We can also run it at lower precision. So if your application works in 4-bit resolution, then you can get higher energy efficiency than half a picojoule per Mac. So what this does for our customers is many times they'll be developing their application on a high-performance GPU, and they might be getting a very high frame rate. And then once they try to go and actually deploy that to something like an SCAM IQ, that will crater their performance down to a very low frame rate. And what they can use by going with us is bringing that performance back while staying within a reasonable power budget. So on the left here, we have the performance for these systems where we're providing about the same performance as a high-end GPU. And then instead of drawing 167 watts, we're drawing 2 watts, which is something you can actually fit in a camera system. In this case, the numbers on the left are measured, and then we're actually estimating our own based on SPI simulations and others. And there's also some degree of measurement from our previous prototypes of the matrix multiplying memory. So this gives us GPU performance in an edge form factor. OpenPose is another application that I mentioned before, and you can see that there's a similar result, except that in this case we're actually able to provide higher performance than what you can get with a high-end GPU. So our timeline is we're looking to release software tools and profiler at the end of this year. Or taping out at the end of the year as well, and hoping to sample the prospective customers about mid next year in 2019. And this will be in the form of PCI Express dev boards. This is actually a photograph of one of them with between 1 and 4 IPUs on it. And there's this chip here is actually a switch, so you can talk to all of them. A PCI Express switch, I mean. And then late 2019, we'll be shipping in volume in the form of BGA chips. So this is flip chip BGA, and PCI Express cards going up to 16 IPUs. So in summary, Mythic is providing a high-performance IPU for edge inference. We're low latency, so we run batch size of 1, which means that we have only a single frame delay on our compute. We're high performance, going up to tens of teramax. High efficiency, so half a picojoule per Mac or 500 milliwatts per teramac, which is also 4 tops per watt is another way of thinking of it. Hyper scalable, so we can do a small chip that's really low power. We can do a large reticle sized chip that's high performance. And then I think this is the one that our customers are actually most interested in. So we're topology agnostic. So we support CNN, DNN, and RNN equally as well. A lot of other systems, if you try to go to RNN, you take about a 4x hit in performance. And then we support all the major platforms like TensorFlow, Caffe2, PyTorch, and so on. So thank you.
So if it wasn't already obvious, IPU is Intelligent Processing Unit, not to be confused with your CPU, which is not intelligent. Okay, so This leads to a lot of questions, so I'd like to open the floor for questions. Okay.
So it seems that, if I understand it correctly, your chip is kind of physically embedding the neural network. Does this remove the possibility of like online updating your model as time goes on, stuff like that Tesla is doing?
No, it does not remove that. So you can update the weights. You need to reprogram them, which takes about a minute. So you can't swap out applications on the fly, but most applications, that's not really a concern. Usually you have a fixed set. Like in Tesla's case, it's not like they're swapping out your neural networks while you're driving down the road.
So one of the things that I noticed in your talk was you talked about like matrices who tend to have like a very large weight matrix. For some of the newer applications that like MobileNet, which use like depthwise separable convolutions and might not have as many weight matrices, do you still see those same performance improvements if the, let's say the, as you call them, the intermediate products are much more, are significantly larger than the weights themselves?
So the energy efficiency and the performance is going to depend on the topology of the network that you use. We found that in our research, many of these cases, there's lots of ideas out there for different ways of improving the network, and a lot of times things tend to shift. You know, initially you introduce an idea, make things very complex, and then over time you end up going back to something that's really simple. And so you tend to see this sort of cyclical process. I think at the end, you know, for these networks, you'll end up seeing simpler ones that map to this style of computing very efficiently, will also be just as accurate as ones that are these more complex neural networks. So for example, if you look at Tacotron and then Tacotron 2, Tacotron True is like 2 is a lot simpler than Tacotron was.
As Eli pointed out, we haven't thought about directly computing in analog for a long time, so we haven't thought too much about the alternative that the world is analog, the signals that come in are analog. We just take it as a matter of course that we have to convert them to digital. But since you're operating analog, have you thought about maybe speech or for vision processing, just operating directly on analog signals?
Yeah, actually, in my last paper in grad school was for doing analog compute directly in an image sensor, and what I found in that case is you can do the first layer of your convolutions in analog, but then after that you'll want to go back to digital again anyway. So you might have, say, like ResNet 50 has a 50-layer neural network. You might get your first layer in analog, and then you're either back into digital, or there's actually another startup out there, Sentient, that's doing an all-analog neural network instead of doing mixed-signal like we are. And that might be a better case for doing audio in the analog domain.
So you mentioned that your chip is sort of architecture agnostic with respect to RNN. So you quoted numbers for CNNs. So can you quote any for RNNs, like in terms of energy improvements or anything?
The energy efficiency for RNN is the same as it is for CNN. So it's a half a picojoule per Mach, regardless if it's RNN, CNN, or dense. But for other systems, you usually see about a 4x hit in energy efficiency and performance by using RNN and dense. So you could say that that's a place where we can get a further 4x boost over competing systems.
Thanks.
Hi, very interesting. Thank you for sharing this with us. For the analog MAC circuits, it seems like you might run into tolerance issues at the edges if the weights are very, very small or you're combining things of different scales, you know, much like round-off.
Yeah, so there is a process for how to handle the range of analog compute outputs. You actually see the same thing in an all-digital system. So let's say you're multiplying two 8-bit numbers, you get a 16-bit result, and you're adding up 1,024 of them. So now you have an 18-bit result, but you have to get back to an 8-bit number somehow. So even the all-digital systems have a scaling factor for how do you map that range back. So you go from like a rectified linear to what we're calling a bounded rectified linear function. And so there's a process that we follow for that in our software, but I know people at Google and IBM that also are looking at that problem for similar reasons in the digital domain.
So I just have a quick question regarding the performance. You got down to a half a picojoule per operation, but the competition was at 2 picojoules. That's your digital competition. I would have expected, since you've revolutionized everything, you'd get more than a factor 4 improvement. So what am I missing?
It's a good question. So the 2 picojoules per Mac isn't measured, so first of all, but neither is our half a picojoule per Mac. I think what you're seeing is that in those systems, 2 picojoules per Mac is a highly optimized 7 nanometer, big team, getting a lot of stuff done type of number. Whereas for analog compute, this is the very first generation. I haven't mentioned here we're not using the DAC on the input. We're using a digital approximation that costs us about a factor of 4 in terms of energy efficiency and performance. We're doing it in 40 nanometer instead of 10, so we go down to 10, we get about another factor of 3. So there's all these big improvements that are available to analog compute that aren't available to digital.
Quick question. So you mentioned your chip is agnostic to the architecture. So are there other startups who are developing accelerators for a particular model and tying it to the exact use case? And how do you compare your energy efficiency numbers with respect to that specialized chip?
So I haven't seen any systems that are specializing in, say, like RNN or dense. And that's because there's nothing to take advantage of. So there's a lot of focus on CNN because you can take advantage of the reuse of the weights. And even if you look at, like, a long time ago, MIT published a paper called IRIS. And you actually see, if you go to ISSCC, you'll see a lot of papers about how they ran the first 5 stages of AlexNet. Those first 5 stages are convolutional. The ones after those first 5 are fully connected, are dense. And so I haven't seen any papers that specialize in those other 2.
Question going back down to the cell. The model you gave was looked like a purely resistive one. What happens if you include reactive parasitics, and sort of how does that affect dynamic behavior, especially relative to the DAC dynamic behavior and the A to D dynamic behavior?
So we do let it. So from a transient point of view, we do let it settle. So from a DC analysis standpoint, like what if it's not perfectly linear and it's curved? The neural networks can learn around those curves. I think if you look at just not even compute, like hardware compute, but neural networks in general, you have like sigmoid function and the rectified linear, and then the leaky rectified linear, and all of these things. And at the end of the day, the thing that neural networks really need is a nonlinear function so some sort of like kink in it, and then some way of resolving a range of outputs. And then after that, it really doesn't care that much. So from what we've seen, if we had like a nonlinear compute element in there that maybe had like a curve to it, that would be okay.
So the final question, I'm looking for a car, but I want it to have all the smarts in it, and you're not shipping your chip until the end of 2019, so that won't get designed into a car. So I'm going to have to wait until 2023 to get this in a car. What do you say about that? To make it a more technical question, what about all your competitors that might be in ahead of you?
That's a good question. So the competition I mentioned before, that was like the 2 picojoules per Mac, that was an enterprise space, and they won't be in those cars. Yeah. So I think right now those vehicles are stuck with pretty much what's out there today, with some improvements out there coming from ARM and NVIDIA soon. But you're just going to have to wait, I guess.
Okay. All right, let's thank our speaker again.
Thank you for having me.